Thank you very much, Mariusz. So it's a great pleasure to be here, and I want to thank the organizer and the IAS for the kind invitation. So let me first present you the three types of objects I will be playing with during this talk. So the first object is a bounded sequence. So you bounded sequence which takes value in the unit disk, the complex unit disk. Okay. So if you insist to see some multiplicative number theory in my talk, you can think of U as being, for example, the Liouville function or the Möbius function, or your favorite multiplicative function. But in all my talk, I will not use any assumption of multiplicativity. So just in any bounded sequence. So the second type of object I will use is the topological dynamical systems. Okay, so these are objects from xt, where X is a compact metric space. And T is a homeomorphism on X. Okay. And the third type of object is a measure preserving system. Which is something of the form X in P. So X is a maybe Polish space. But in most of the examples, it will also be a compact space. So mu is a probability measure on the Borel sigma-algebra of X, and T is an invertible measure preserving and measurable transformation on X. Okay. Okay, so there are some connections between the three types of objects which I will use constantly. So, for example, you can use topological dynamical system to produce sequences. For example, if you have xt here and you take some f which is continuous on x, and some point x in the space, you can consider the sequence f of t and x. Okay, you can also go from topological dynamical system to measure preserving systems by simply choosing an invariant measure on X. Okay, so I will just comment a little bit more on the choice of the invariant measures later. And what is maybe more fundamental in my talk, how you come from a bounded sequence to a measure preserving system. On this, you do it by what we call a Furstenberg system of the bounded sequence, which I will justify in a second. Okay, so just concerning invariant measures on your topological system, the classical way to provide invariant measures is the following. You pick a point X in the compact metric space X, and you consider these averages. So I put Dirac masses on the first point of the orbit of X, and I average all these Dirac masses. So this is a probability measure in the space of probability measure on X. So this space being compact for the Weikster topology, we can always choose some subsequence so that this converges, so subsequence nk, such that this converge as gate go to infinity to some, so this is in a Weikster sense, to some invariant measure kappa. And then you get some measure preserving system. Okay, so when this happens, so I will say that kappa is a visible measure from X. So here I will, if I can find some subsequence nk, so that this happens, I will say that kappa is in VT of the point X. And given a topological system, I will consider all the measures I can access through this procedure, and we will call them visible measures. Okay, so this is the union for all X and X of VT of X. So this is included in the set of all invariant measures in the set, but in general, it is smaller. Okay. You can easily build examples where there are invariant measures which are not visible in this. Okay. And now, what about Furstenberg systems of a sequence U? So I have my sequence U, and so if necessary, I will extend it to the negative integers arbitrarily. But in a bounded manner, of course, so that I see U as a point in the space of all B infinite sequences in the unit disk. And then on this compact metric space, I put the shift map, which I denote by S. So I see U in a special topological dynamical system. And then I can use this procedure starting from U and see all measures which are visible from it. Okay. And then, so if you take kappa in VS of U, then you get some shift invariant probability measure on the set of sequences. And you get a measure preserving system, which I call a Furstenberg system of U. Okay. And this Furstenberg system encodes a lot of statistical properties of the sequence you are studying. Okay, so now the motivation for our study is Sarnak conjecture, which Thierry already recalled, but I will state it again. Okay, I will state it for the Liouville function. Okay, in particular, this avoids the confusion with the symbol mu, which I usually use for the measure. So, Sarnak conjecture is the following: for all dynamical system, topological dynamical system with topological entropy is 0 for each point, for each continuous function on the space. So you have no correlation between the sequence provided by this f on x on the Liouville function. So this averages go to 0. Okay. this property, in short, I will write it this way: lambda is orthogonal to the class of all zero entropy topological systems. And I will find more precisely this notation in a wider context later. Okay, so the question we asked on this conjecture is the following: how could we possibly characterize this result just by intrinsic properties of the sequence lambda? Okay, so can we find intrinsic properties of lambda which ensure the validity of such disjunctions? So there are well-known such properties. In particular, Peter Sarnak already mentioned that the famous Chaola conjecture implies this. Okay, so this is some intrinsic property of lambda which would imply this orthogonality. So this is Chaola conjecture. So you look at all multiple correlation of the real function. So maybe I should take a finite subset of the integers. Okay, and then I consider all these averages. I do the product for all j and f. From that n plus j, and this is supposed to go to 0. Okay, so it is now well known that if Chaola is true, then Sarnak conjecture is true. But in fact, this property is in some sense much too strong for Sarnak. By this, I mean that we can easily find some sequences taking values in -1, 1, for which Chaola property fails, but which satisfies Sarnak orthogonality condition. So I will now introduce by Veech. So this is Veech property. Veech conjecture that this property was true for the Liouville or the Möbius function. Okay, I will state it for the Liouville function. And this is the following property. You take any Furstenberg system of lambda. And once you have such a Furstenberg system, you consider the following. So you take so psi 0 will be we are in this system now u to the z, the shift map on our measure preserving kappa. And psi 0 is just the evaluation of the 0 coordinate in the set of sequences. Okay. Okay, so now I consider the conditional expectation of this coordinate with respect to some special sigma-algebra, which is the Pinsker sigma-algebra in the system. Okay. And we denote it by pi of kappa. So pi of kappa is the Pinsker sigma-algebra. By definition, this is the largest S-invariant sigma-algebra in the system, on which the action of the shift map gives rise to a zero entropy measure preserving system. Largest S-invariant sub-sigma-algebra. The action of S 0. So now it's the log of C9 entropy. Okay. So Veech considers this conditional expectation, and he conjectures that this is always 0 for any Furstenberg system of the Liouville function. Okay. So now this is what Veech proved. So Veech implies Sarnak conjecture. Okay, and in fact, well, it's quite easy to see that Joanna implies Veech property. So the Veech property is somewhere between Joanna and Sarnak, and Veech asked where this property exactly is. So
can you say a word about Furstenberg's disjointness of positive entropy systems or case systems from 0 entropy lies in this picture? I mean, it's
I will
you'll return to that.
I will explain this later.
Okay, thanks.
Yes, of course, this is a fundamental ingredient in this theorem. Okay, so in the rest of this talk, which is based on a joint work, so with Joanna, Kułaga-Przymus, Adam Kanigowski, and Mariusz Lemańczyk. I will give you a proof of Veech theorem. Then I will prove that, in fact, those two properties are equivalent. So show you why the converse is true.
Did Veech expect that? You know?
It's not clear. It's not clear. He does not explicitly write this in his notes. He conjectures that this property is true, and he says that this property is between Joanna and Sarnak, and he just asks where is it.
Okay. Yeah. Interesting.
Okay. And I will do all this in a much larger context than just in this question. So by larger context, I mean that I will not specify the sequence I'm interested in, so it will be any bounded sequence U, and I will possibly replace the 0 entropy property, which we use in these conjectures, by some other properties of dynamical system. So this is now what I will talk about. So what is the central element in this Veech property? So this is the Pinsker sigma-algebra. Okay, so this is, as I said, this is the largest factor with 0 entropy, and this sigma-algebra has nice property in the sense that it controls all joinings that you can make with any other 0 entropy measure system. Okay, so it turns out that there are many classes of measure observing systems for which we can provide this kind of largest sigma-algebra with nice properties. And this is exactly what I will introduce now. So these are characteristic classes. So these are classes of measure observing systems. Okay, so I will say that a class F of measure preserving system is characteristic. If it is stable under isomorphisms, more or less implicit in such a definition, taking factor. So if I have a system in the class S, and if I consider a factor, then this factor is also in the class F, and taking countable joinings. Okay, by this, I mean that a way of saying this is that if you have a measure preserving system, and if its Borel sigma-algebra is generated by countably many invariant sigma-algebra on which the transformation is in the class F, then the whole system is also in the class F. Okay, so let me maybe give some examples of such characteristics. Okay, there are many examples, but there are some which are quite classical. So the first one, which is of interest in these questions, is zero entropy. Okay. Okay, so I will denote it by ZE. So this zero entropy property is stable by taking vectors and taking countable joinings. This is classical ergodic theory. Okay, so other nice classes of systems maybe is a quite easy one is the class of all systems with identity for the transformation. Okay, I will denote it by id. Okay, maybe some other nice classes. Another nice class is the class of measure preserving system with discrete spectrum, for example. Okay, by disp on a very important family of classes, which has been introduced by Bernard Rost and Mariusz, their theory, which are nil systems. Okay. Okay, I should say more precisely. I denote by nil S the class of all measure preserving systems, which are inverse limits of nil systems of order S. More precisely, sorry. Every ergodic, almost every ergodic component is an inverse limit of nil system of order. So this is the S, which is also a characteristic. Okay, so once we have defined this characteristic classes, let me tell you about there are nice properties. So whenever you have some characteristic class of measure preserving systems, we have the existence of largest sigma algebra in the same sense of as in the zero entropy sense. So this is property one. So if F is a characteristic class, any measure preserving system, there exists the largest factor sigma-algebra, which okay, I will denote by AF. So AF sigma-algebra of X. Okay, and it is the largest, so in the sense of inclusion of sigma-algebra, and on which direction of T find factor the class F. Okay, so this is exactly what happens for the Pinsker sigma-algebra in the class of zero entropy, but this happens in every characteristic class. Okay. And, indeed, in all the examples I gave you, these largest factor sigma-algebra are classical objects in algebraic theory. So I already said what is the largest factor in the zero entropy class. So this is the Pinsker factor. Okay. So in the class of identities, what is the largest factor on which the action of the transformation is the identity? It is just the sigma-algebra of invariant subsets. Okay, so in the class of the discrete spectrum class, so the largest F sigma-algebra is just what we call the Kronecker factor. And in the class of nil S, the largest sigma-algebra is the structure factor of order S introduced by Post and Kahn. Which is usually denoted by CS. Okay. So this is the first property of characteristic class. And the second one is a nice property of this largest factor with respect to joining. And I will state it below. So I take any measure preserving system X mu T, and I consider another system which I assume is in the characteristic class F. And I consider a joining between this arbitrary system and the F system 1. Okay. Rho is the joining of these two systems. Okay, maybe I should recall what is the joining. So joining two systems is just, so we have the Cartesian product of X and Y. And I have this measure Y, I have this measure U. And rho is a probability measure on the Cartesian product, which projects on mu and nu, and which is invariant by the product transformation. So this rho defines the largest system in which the two X and Y are factors. Okay, so for any joinings of these two systems, so this relatively independent above the largest F factor in X. Okay, so what do I mean by relatively independent? Well, one way to characterize this is the following. So take some function f in x or in L2 of mu, and assume that the conditional expectation of f with respect to this largest factor is 0. So we have this. Then this function has no correlation with any function in the segment system which is in the class F. Okay, so any correlation between x and some F system should go through this maximal factor. Okay. Then for each g, which is defined now on the wall here, L2 of mu, if I take the expectation of the tensor product f times g, then g. Okay. So this is the nice property which we use on. This is used in particular in the Furstenberg result between zero entropy on K systems, for example. Okay. So now I think I have all the tools to prove you the theorem of Veech, which is still here.
I think of proposition 1 and proposition 2 as being sort of obvious, or is there some work you have to do to prove?
No, there is some work. Okay, the first proposition is quite simple. For the first one, it's relatively simple. You consider all the sets, which you find action in class F, and you use stability by joining.
You need some sort of counter saturation or something.
Yeah, something like that. Okay, for the second one, it is a little bit more subtle. It needs some results about joinings which are not product measure. Okay, to do some machinery.
Disintegration and stuff. Is it just like disintegration and stuff, or do you need something?
No, it's more subtle. Okay, I will not give details on that. Take it as a black box, but I come to speak after. Okay, so now what is the proof of Veech theorem? Okay, maybe I should, before introduce more generally Veech property for class F, sorry. So okay, I forgot something. Okay, now that we have this maximal F factor, so we can define Veech property. This is the following property. So for each Furstenberg system of our sequence U, we have a conditional expectation of the zero coordinate with respect to the maximal F factor is 0. So this is Veech property in general. And okay, I also have to introduce the topological counterpart of this class, characteristic class. So once I have a characteristic class of measure preserving system, which is F, so I will use this notation, CF, to denote the class of all topological dynamical system. in which all visible measures, in the sense that I defined here, give rise to systems in the class F. Okay. So in particular, you may observe that if I start with a zero entropy class, then I get exactly the class of all topological systems which have zero topological entropy. Okay, so now this is Veech theorem in this more general setting. So if each property of the class F, so this is if this property is true, then U is orthogonal to all system in the CF class. Which, okay, this means that for any X on any continuous function of some F system in CF, we have no correlation. Okay, so let me give you a quick proof of that now. Okay, so I take CF and I want to evaluate these averages. So for some X and F continuous function. Okay, so what we do is okay, we consider any subsequence nk. Okay. This is an increasing sequence of integer, and I can always assume, if necessary, I just extract some subsequence. I can assume that I have convergence of empirical measures, which I write now. So I will consider these empirical measures. So in the product, u to the z times x. So I have two coordinates. The first one, I apply the shift map. On the second one, I apply the transformation T. So I consider these empirical measures, and I can extract a subsequence such that these empirical measures converge. On what could be the possible limit? So the limit will be some measure on the product. On the first coordinate, I will get some Furstenberg system of the sequence U. Okay, so rho will be a joining of kappa, which is a Furstenberg system of U, and of some measure which is visible from X in the second system. So say U, which is VT of, okay. So now I use the fact that my system xt is in CF, so it means that this measure nu here which is a visible measure. So it gives rise to a measure preserving system in the class F. We have that y, x ut in F. So I have a joining with some F system. I can use maybe property 2, which is that's here. Since I have a joining with some F system on, I assume that which property holds for the sequence U, which is exactly this one. So by property 2, I have that the condition, sorry, the product, the tensor product I0 and F for the joining row has 0 expectation. Okay, but then if I consider this special sequence, this precisely converges to the integral of this expectation sin 0 sin f. So this is okay. So from any sequence nk, I can extract some subsequence so that this converges to 0. So the limit must be 0. Okay. So this is the strategy of the Veech theorem. Okay. So do I have time to say something about the converse? Or
I have a little question here, because when I was looking at this many years ago, there was always the issue of assuming that you're generic for some system. Somehow this is now captured where? You know what I'm talking about?
Yeah, okay. Well, you know that you are quasi-generic along some subsequence. Okay, the Veech property is strong in the sense that you assume that for any system for which you are quasi-generic, you have this property.
I see.
This is where it is given. Okay. Okay, so maybe I will not give too much detail about the converse, except that the converse is, well, we are not able to prove the converse in any characteristic class, but just in some particular characteristic class. So we'll just precise what is the statement, the converse statement. So, given a characteristic class F, we introduce an associated characteristic class, which we denote by FEC. Okay, so it is a class of measure preserving systems for which almost all ergodic components give systems which are in F. Okay, so there is some subtlety between F and FEC, and there is no general relation between those two classes. This is always a characteristic class too. Okay, so sometimes they coincide, sometimes one is included in the other, but it can be both ways. And okay, we say that F is an EC class if F coincides with FEC. Okay, so this is the case for the zero entropy class. Okay. Okay, and then for all FEC class, for all EC classes, the converse of Veech theorem is true. Okay. So this is the statement. if F an EC class, then if we have orthogonality of some sequence with respect to all systems in the class F, then each property with respect to F for you is true. Okay. So this converse is much more difficult on the first implication, and it uses a lot of technicality in ergodic theory. So I will not have time to detail on this now. Maybe what I could do now is just give you some combinatorial interpretation of Veech property in the case of the zero entropy class.
The characteristic class
Sorry?
is not an ergodic component class. And is example of a class that is not on this category.
Yes, for example, the discrete spectrum class.
Discrete spectrum.
Okay, you can,
Without
okay, it's not because you may have all ergodic components with discrete spectrum, but
not.
the whole system is not.
But you think it's true on in full generality? You think it's true?
It's not clear because there are several points in the proof where we use explicitly that we have EC classes. Don't see any reason why this shouldn't be true, but our proof doesn't work in general. Okay, so now we have this property, which is this property in the zero entropy class. How can we interpret this combinatorially on the sequence? So this is this property for the zero entropy. Okay, so I will just assume in this part that U takes finitely many values. So assume finitely many values, and this is essential for the following remarks. That in this case, other question. Then in this case, for any Furstenberg system of U, the Pinsker algebra of kappa is the intersection. It is the tail sigma algebra of the coordinates. So I take the intersection for all the N of the sigma algebra generated by the coordinates n plus 1. So this is the part where the finitely many values is important. Okay, so now Veech property is just saying that conditional expectation given this sigma algebra, okay, by the martingale theorem, this converges to the conditional expectation with respect to the Pinsker factor. So this property says that this go to 0 and go to infinity. Maybe I will use M. Okay, so maybe we could characterize this by the following. For any function which is bounded by 1, so you take the product between psi 0 and this function of psi m can take the supremum for all f bounded by 1 of this product, or this go to 0 as m go to infinity. Okay. So now, if we come back to our sequence view on the definition of the Furstenberg system. Okay, so maybe just before, okay, by some density argument, we can restrict ourselves here to function which depends only on finitely many coordinates here. Okay. Okay. So this gives the following, just for sequence new. So this Furstenberg system is given by an increasing sequence of integers, nk. So for any increasing sequence nk, a Furstenberg system of u, we have the following. Supremum for all function f depending infinitely of 1 over nk. So I take u of n on f of this. U of n plus n plus m plus 1. So this supremum, when I take the limit, so this gives me the expectation with respect to kappa. On this, go to 0 as m go to infinity. Okay. So this is not very beautiful, but this is what we get. Combinatorial characterization of this property. Just to finish, just assume that the sequence u takes values in -1, 1. Okay. And then I will take some special functions depending on finitely many coordinates. Just take the product of finitely many coordinates. Okay, and what we get is the following. You have the supremum for all function f, for all f which is finite in n. For this, so we have limit as k equal to infinity, 1 over nk. So we sum over n, and we have n times the product of u of n, sorry, n, okay. So this should go to 0 as n go to infinity. So we get some kind of Chaula type property, but this is an asymptotic Chaula with the first gap, which is very large. So this is not actually exactly the same as Veech property. So in fact, Veech property implies this one, but we don't know if in the case of two values -1 on 1, the converse implication is 2. Okay, it's not clear. Try to find some counterexample, but it's not all. Okay, so I will finish here.
Do we have some questions, comments?
So it's a potential strong Veech property where you don't assume that the projection is orthogonal to the Pinsker factor, but you assume the Pinsker factor is trivial. This is stronger than.
Of course. Yeah.
Is it known to not be equivalent?
Yes, we have examples where the Pinsker factor is not trivial, but yet you have some example in mind?
The question is on the abstract level for every.
Yes, of course. For every.
You will have something.
Hmm?
It's not the same.
No, but do you have a precise counterexample in mind or? Okay.
But it's going to exist some.
Well, yeah, I'm quite sure that it exists. Okay, well, just think a few minutes and I will give you. Okay, just.
I'll escalate.
Can you not just take your product system? Like rotation and Bernoulli?
Well, I want the sequence.
I want the sequence.
Yeah.
It's generic for something like that. Sorry.
Okay.
I had a question about this class of topological systems CF and how different this class becomes if you consider measures that are not necessarily visible measures. So is it clear that, for example, take the class of zero entropy, F is the zero entropy, measurable zero entropy class that you define over here. Is it true that, for example, topological entropy is the supremum over measurable entropy over measures that are visible, or in this sense that you define them?
Okay, I see the sense of your question. Entropy is not that clear. But sure, in the proof, we do really use the fact that all measures we are using are visible. Okay, it's important at many places in the proof. So now, okay, we should probably find some examples.
Yes.
Differences.
Right. I guess. Do you get? Does this change substantially? Maybe if you say all measures, not just the visible ones, that belong to this class F, or is it possible that say all visible measures belong to this class F and it's a characteristic class, then all invariant measures?
No, there are for example, in the discrete spectrum case, we have examples where all visible measures have discrete spectrum, but you have invariant measures which do not have discrete spectrum.
Already in that class. Yeah. Okay. Okay. I'll think about it a little more. Maybe it's possible that EC classes have this property, or maybe.
Yes, for EC class, no, same problem.
Same problem. Okay. Thanks.
More questions?
One very quick follow-up. So do you have an explicit example of a characteristic class for which you cannot prove the converse? Discrete spectrum, you can prove it?
In the class of discrete spectrums, this is the only example of non-EC class for which we are able to prove the converse.
Okay.
For nil systems, it's already not clear.
Well, nil systems, these are EC class. By definition, nil systems, you consider only the ergodic components. So for nil systems, it works perfectly.
Clever definition.
Okay, so if we don't have more questions, so let's thank the speaker again.